section or something. So
is there a track it for this, or?
There is a track it, but we're not going to use the track it in the meeting right now. The track it is really just for archival purposes, but we will get you all the ID and stuff for that later. However, you did just remind me I need to drop in the chat the link to this this observable notebook. So if you see that link with observablehq.com that I just posted in there, you're going to want to go ahead and click that and open it in a web browser, and you should see a spinning cube and a lot of code and a lot of text. And if you don't, then let me know in the chat.
Before you start, Matt, can you start recording?
It's been recording. Yes, it's been recording.
I can't tell. That's why. Okay, sounds good.
All right, cool. Well, thank you, Matthew, for getting that started. We're going to go ahead and start now, I guess. So, yeah, if you've ever wondered how your computer draws 3D images, it's actually a relatively complicated process because it involves a lot of communication between your CPU, where your JavaScript code runs, and your GPU, which is very fast for like filling in polygons and drawing pixels on the screen, but it's not so fast for doing like general purpose calculations. So the two processors actually have to work together. And WebGL stands for Web Graphics Library. That's basically an API that we can access through our web browser through JavaScript that lets us communicate from the JavaScript code that runs on our CPU to the GPU. So we can send it commands to draw triangles and also all sorts of interesting objects, and how to fill in the triangles with different colors and all that. So I'm going to go ahead and get started with a quick overview of the graphics pipeline so we can talk about the different stages that the GPU performs, like different types of processing, right, before you actually get your final triangle on the screen. And we're going to be talking about it just with one triangle for now, but don't worry, because once you can do it with one triangle, you can do it with hundreds or thousands or millions, however many your computer supports. So yeah, so here's a quick overview of how the graphics pipeline in OpenGL, which is basically WebGL, how it works. And basically, so our first input, right, is going to be the triangles that form the 3D model. So every 3D model, every 3D object on your screen is made of a bunch of polygons. And normally triangles, right? Because those are the easiest for a computer to process. If you have a square, you just cut it up into 2 triangles. And we have to store those somewhere in memory. So these are stored in geometry buffers. So there are 2 types of those, are vertex buffers and index buffers. And vertex buffers, they store vertex positions and other attributes of vertices. So for example, maybe your texture coordinates and your normals, which are used for drawing textures and lighting, and we'll talk about that later. In a single chunk of GPU accessible memory. So basically, there's a lot of numbers, right, in a long array that indicates all the different coordinates of the vertices of the model you're trying to draw, and we have to put those all next to each other in a big chunk of memory that is easy for the graphics card to access. And that's basically what a buffer is. It's just a chunk of memory that contains meaningful data. In this case, the meaningful data is the data for the object that we want to draw. You also have index buffers. So a lot of times in a more complicated model, but even with the cube, right, there's multiple triangles that will share the same vertex. And so what index buffers do is they let us reference vertices just by a number that indicates their ID. So we can draw them, we can reuse them across multiple triangles in the object. And I'm sorry if that's confusing. Hopefully you understand, but if not, drop a question in the chat and I will go into it in more detail later. I'll actually show you what kind of content we put inside an index buffer. The next stage is the Vertex Shader. So the Vertex Shader basically takes in every vertex in our buffer, and it is going to take its coordinates in 3D world space. So that is the basically, the cube. So these coordinates are from -1 on the left of the cube to 1 on the right of the cube, and like -1 on the bottom to the top of the cube, right? But these do not match exactly into 2-dimensional coordinates that we would draw on the screen, right? So the Vertex Shader is what we use to transform the vertices so that they will display in the appropriate locations on the screen, right? So it basically projects from 3-dimensional space into 2-dimensional space. Now, the shape assembly stage is pretty simple. It's not really something you have to worry about because it basically automatically happens. just by pushing your buffers to the GPU and telling it to draw them. But the shape assembly stage basically takes the 3 vertices and it will turn them into a triangle. And it will do that over and over for as many triangles as you have in the model. The geometry shader, we don't need to worry about that because it does not exist in WebGL. It only exists in sort of your native C++ desktop OpenGL. We then have the rasterization stage. So rasterization is it's called rasterization because we're taking vector data or vertices, right, points in space, and we're turning it into raster data. So raster data is like a bitmap. It's basically the final 2D image that gets written out to your screen. And yes, GPUs are very good at rasterization. That's why we have a separate processor to a GPU, graphics processing unit, to render our graphics, is because it's a lot more efficient than a CPU at rastering lots of triangles in one go. And the Fragment Shader is a piece of code similar to the Vertex Shader. I forgot to mention earlier, both types of shaders run on the GPU rather than the CPU. And they're written in a special programming language called GLSL, GL shading language, which we'll cover soon. But the Fragment Shader basically determines what every single pixel is colored, determines the color of every pixel. And then test and blending, finally. Basically, the idea of testing, the most common test we're going to use is the depth test. And that basically makes sure that objects that are in the background are not drawn on top of objects in the foreground. So it ensures that everything is drawn correctly such that objects in front obscure objects behind. There's also alpha testing and alpha blending if you want to composite multiple transparent objects or a combination of transparent and opaque objects. But that can get a little bit difficult to configure. So we're not going to cover that in this workshop here. I'm going to be checking the chat shortly for questions. So let me know if there's any questions. Jafar asked, shape assembly runs on the CPU and rasterization happens on the GPU. Great question, but not exactly. Shape assembly actually happens on the GPU as well. I can see why you'd be confused about that though. So the only thing that we, in this pipeline that we do on the CPU is transferring the vertex buffers to GPU memory and compiling the vertex and fragment shaders. Other than that, everything in this pipeline happens on the GPU. So shape assembly would happen on the GPU as well. Yeah, let me know if there's any other questions. Drop them in the chat. Otherwise, I'll just continue with talking about shaders. So yes, let's start with a vertex shader. So vertex shaders are often pretty simple. You can do complicated effects like, you know, making a sort of like watery wave effects and stuff by manipulating vertices, but we're not going to worry about that for now. That's kind of like an edge case, right? So the most basic vertex shader is going to take in an attribute, which is the position of a vertex. Attributes are specified on a per vertex basis. So when you have attributes in your shader, that means every vertex of your model is going to have that property. In this case, we only have one property, and that's the position property, or the position attribute, right, to use GLSL terminology. And that's just a vec3. So a vec3 is a 3-dimensional vector. You'll see there's also vec4s, which are 4-dimensional vectors, vec2s, which are 2-dimensional, etc. We also have these things called uniforms. So uniforms are not set on a per vertex basis, but they are set on a per draw call basis, which you can think of almost as a per frame basis, right? So every time you call the shader to render a model, you can upload new data into that uniform slot once, and then it's going to stay the same or stay uniform, right? For the entire time the shader runs, the model is drawn, and the next time you draw a different model, you can update it again. So the two uniforms we have in this shader are the projection matrix and the model view matrix. And the projection matrix in our case is going to apply a perspective transform. So if you multiply a vertex position by the projection matrix, then that is the main matrix that is in charge of transforming from 3D to 2D. So it will take a 3D position and it will, it will sort of push it towards the middle of the screen. So it looks like it's shrinking in if it's far away. If the Z coordinate is far away, it will pull it out closer to you, right? If it's closer. And that's what creates the perspective effect of sort of things farther away being smaller than things up close. The model view matrix is, we have two matrices that we're going to talk about here, the model matrix and the view matrix. And those will be computed on the CPU. I'll go into detail about those a little bit later. But the model view matrix is the product of the two matrices. So when you want to determine the position of the matrix, we take the projection matrix times the model view matrix times the position of the vertex, the input position of the vertex, and that gives us our output position on the screen. GL position is a built-in variable, and and when we assign a value to GL position, that actually that basically tells the GPU, hey, this is the final position of the vertex, this is where we want you to put it on the screen. And we use a 4-dimensional vector here with position because we're multiplying by 4-dimensional matrices. That just seems to be a convention in computer graphics. I don't know enough about the exact math behind it to explain why that is, but you can read about it online. And here again, if you want a more detailed technical overview, you're welcome to always read the content of this notebook, and I'll make sure the links are posted in a prominent location by the end of this. But here I'm giving you sort of a more theoretical overview. The fragment shader basically determines the color of every single pixel in the object, right? So we rasterize our triangle, and then now that we know what pixels on the screen we want to fill in for the triangle, we have to determine a color for every single one of those pixels. And the fragment shader is in charge of determining that color. In our case, because we're trying to keep stuff really simple, we're just going to assign the same value to every pixel. And that value is 0.9, so 90% red, 40% green, and 60% blue. And so your RGB values here, they range from 0 to 1 instead of 0 to 255. So if you're coming from like Photoshop or Paint or something, then it's going to be a little bit different. And yeah, so that's a very basic fragment shader. We'll create a more advanced one later in the workshop. But I'm going to take a moment to answer any questions now. So I'm going to check the chat. We covered draw call batching. Okay, I really like that question from Hayden there. So draw call batching, this gets into a little more advanced stuff than we are going to cover in the workshop right now, because we're really just trying to teach people how to basically create their first draw call. But if you want to talk about draw call batching with me later, just hit me up on Discord. I will post my Discord ID in the chat, and that goes for anyone else, right? So if you want to talk about other stuff that we don't cover in the workshop, let me know. So this process runs before the rendering phase we discussed before. This is a process needed to get the vertex buffer data. Jafar, were you talking about the vertex shader when you asked that question? Jafar, are you there?
Yeah. I think that's the name of it. Sorry.
Yeah.
It
so
was a step before when you took 3D space and you converted it into a 2D like shape. Through matrices.
Yes. This process. Yeah, you're right. That's a great question. So this process does run before rasterization happens.
Okay.
So before we start filling in pixels, we got to project the vertices into the appropriate positions in screen space, and then we'll fill in those pixels on the screen.
And this stuff happens on the CPU.
No, so the vertex shader runs on the GPU.
Oh,
so
okay.
by the time yeah. Sorry, I'm going a little bit out of order here, but it's going to make sense soon. Yeah, that's a really good question. But the only thing that happens on the CPU is pushing the vertices and pushing the shaders to the GPU, and then the actual transformation of the vertices in the vertex shader will be executed on the GPU once it has the necessary information.
I see. Thank you.
Yeah, you're welcome. Niranjan asked, can you go over what the numbers represent in frag color? So yeah, I think that's what I tried to explain before, that these different this is basically a red component, this is your green component, this is your blue component, and this is alpha or opacity. In this case, we always use 1.0 because we're not rendering anything transparent. So let me know if that answers your question. All right, cool. It does. Yeah, thank you everyone for the questions. Definitely keep them coming while we go through this content. So I wrote some utility functions here to make life easier for us, and one of them is the compile shader function. So basically, when we write our shaders here, you see this is human readable code, right? Like we can understand what this does, but that's not very efficient for processors to execute, right? Processors have to execute bytecode. So all of this has to be turned into just like a big stream of bytes that then are like meaningful instructions that a processor can execute. If you're familiar with compiling a C++ program so that it runs natively on the CPU, this is basically like a language that turns into native GPU code. So the compile shader function uses WebGL's APIs for shader compilation. So first we have to ask WebGL to give us a shader resource. All resources in WebGL have to be allocated explicitly. So we have to ask it to give us a resource, and we have to delete it when we're done with it, or it will automatically be deleted like when you close the browser or something. And then we call shader source. So this function, basically we take our source code. So this argument is a string that has the source code for the shader, and we pass it into the shader source function. And then we just call compile shader. And this line right here takes our textual human readable code and turns it into bytecode that a GPU can execute very, very quickly. So it's very efficient. And we also have a little check for the edge case that our shader didn't compile. If we made a syntax error, if we mistyped something, then it's really important that we catch it here. And we use gl.getShaderInfoLog to request information about the shader and log it to the browser console so that we can see what went wrong. Yes, I'm not going to go over this, but we will see how to call this function later. Linking shaders. Okay, so two shaders. When you have two shaders, you have a vertex shader and a fragment shader, right? They actually work together to shade the same object. So when you issue a draw call, basically when you tell the GPU draw my triangle for me or my array of triangles, you'll never use a single shader individually. You're always going to use a shader program, which is a vertex and a fragment shader that have been combined together to run together. And so if you're familiar with the process of linking a C++ application, where you have like one C++ source file and another C++ source file, and the two of them have to talk to each other to be able to run the whole application, we're doing a similar thing here. In fact, the terminology we use in WebGL is linking as well, linking the program. So we call the compile shader function the type keyword, the type argument. We pass in either the gl.vertex shader type or gl.fragment shader type to let it know what kind of shader we want to compile. And we pass in the source code as well for the shaders. So these arguments are going to be strings, and I'll show you where the strings come from soon. Then we request a program resource from WebGL. We attach both our vertex and fragment shaders to the program, and then we link the shader program to make it execute. Basically to take our two shader executables and combine them into one full functional shader program. And similarly for how we check for errors in shader compilation, we also check for linking errors here. And if you want a detailed explanation of what all these functions do, then it's down here. Otherwise, we just return the shader program so that we can use it later. Now, we're going to actually try compiling a shader and make sure it worked. So before you can compile anything, we have to get a WebGL context. A WebGL context is basically, it keeps track of all the different resources you've allocated and settings, like GPU configuration settings you've set. So if you enable depth testing, we keep track of that in the context. If you create a shader, the context owns the shader, basically. So you have to have a WebGL context before you can issue any WebGL API calls. And in these functions up here, we actually just took in the WebGL context as an argument. So we're going to have to get the context that we can pass into that function here. So we do that by, we have the canvas element, which we declared all the way up here, right? With the document.createElement function, we create a new canvas element in the web page. And then we go all the way down here. We call it getContext function. And there's multiple types of context you can use. There's a 2D context as well as a WebGL context. Here we want to use the WebGL context. So we pass in the string WebGL, and that tells the browser that we want a WebGL context from our canvas. And then the next thing we do is we call the init shader program function that we wrote above with our vertex shader source and our fragment shader source and our WebGL context. So these variables are actually just the names of the strings we defined above. So when we wrote our shaders and we stored them in variables, the source code and variables, these are those two things. And you can see that we have a valid WebGL program object here after this runs. So this is really our first time we've actually made WebGL API calls, and they came back and they worked, which is really nice. Unfortunately, you still don't have anything cool to see on the screen yet. You don't see anything on the screen until you render the entire cube. So I know It's a lot of content. It's a lot of waiting, but this is telling you that you're basically what you've done so far is correct. I'm going to go ahead and check in the chat now. If you have a question, let us know. Arson asks, so are all of our shaders compiled during runtime? Is there a way to pre-compile them? That is a really good question. Pre-compiling shaders is something that developers that was high in demand for a while, right? People wanted to hide their shader source code and just hope that it would load faster. And so yes, there is a way to pre-compile shaders. However, I believe in WebGL version 1, the first version of WebGL, which is what we're using here, I don't think it supports pre-compiled shaders. But I think WebGL 2 supports pre-compiled shaders, and I know that desktop OpenGL supports pre-compiled shaders, and Vulkan and DirectX 12, which are sort of the next generation graphics APIs that came after WebGL and OpenGL. Those both support pre-compiled shaders. So that's a really good question. Yes, there is a way to pre-compile shaders, but not in the version of WebGL that we are using here. And that's also a really good question because there's a lot of reasons you would want to pre-compile your shaders. That can actually increase the reliability that it'll work across multiple machines. So the graphics driver doesn't make a mistake, right, in compiling your shader source code. All right, so yes, we have our shader program now. Now, find attributes and uniforms in our shader above. We define the position attribute and the projection and model view matrix uniforms. In order to be able to communicate with those attributes and uniforms from JavaScript to the GPU, we have to get their location. So their location is basically a numeric ID, an integer value that represents where they are on the GPU. And we can pass this location into future WebGL calls that you'll see later. We get them with the gl.get attribute location and gl.get uniform location functions. So these functions take in our shader program, and they take in the name of the attribute or uniform that we want to get, and it works. And that's a really important step in being able to transfer data to the shader, so that the shader actually has something meaningful to execute. And you can see when you look here, well, attributes are just an integer. So position is 0 because it's the first one. Uniforms are a special type of WebGL uniform location. So as long as these are not null, they're like a real value, then that means it worked. Or if an attribute is a -1, then that means it didn't work. But we're good. It worked. So now let's talk about geometry buffers. So before we can actually start buffering our geometry to the GPU, we have to we have to have a 3D model, right? We have to have its data that we're going to use. So I stored these in just plain JavaScript arrays, but this is a big long array of the position of every vertex on the cube. So you can see these are the 4 vertices that make up the front face of the cube. So this is the bottom left, this is the top left, this is the top right, and this is the bottom right. No, never mind. This is the top left. This is the top right. This is the bottom right. This is the bottom left, right? You can tell, but because of the sign of the numbers in front, and because the z coordinate is positive, that means it's out in front. But the reason I'm not going into more detail about these is because if you use a 3D modeling application like Blender, there's actually a really straightforward way to just get your geometry values out of it. If you save as a .raw file, which is an option in Blender, that's just raw triangle data, and that basically just gives you a long array like this. So you can actually inspect your 3D model data, and I'd highly encourage you to do that. There's also the indices of our cube, right? So we talked about index arrays earlier, and I think I explained a square in a GPU is made of 2 triangles, right? So how do we get those 2 triangles from only 4 vertices that we've declared here? We actually need 6, right? Well, what we do is the index array has just indices, so basically pointers into the vertex array. So the first 3 vertices we want to use are 0, 1, and 2. So in computing, indices often start from 0 rather than 1. So this is the first, second, and third vertex. Then what we do is the next triangle is made of the first, third, and fourth vertex from the vertex buffer. So instead of having to actually write out 6 vertices up here for the front face, we just wrote out 4, and then we referenced sort of the same ones multiple times, adding in a different one where appropriate for a different face. And then now that we have those JavaScript arrays, though, it would be really inefficient for the GPU to try to read from JavaScript arrays because they're slow, right? They're stored in CPU memory, which is not connected to the GPU in the same way, and they can have any type of data. So if you're familiar with JavaScript, it doesn't have very strict typing regulations, right? Which is a disaster when you're trying to do low-level, high-performance programming. So JavaScript and WebGL have exposed APIs that we can use to convert these arrays into typed arrays. So we're going to make this into an array of floating point values and this into an array of integer values, and then push them into GPU memory. This create buffer utility function performs the step of pushing a typed array into GPU memory. So we allocate our buffer in GPU memory here with gl.createBuffer. We bind the buffer. So with WebGL, often, you won't reference this buffer by its variable name buffer. You reference it by the target you bind it to, which in this case is gl.arrayBuffer. That will be an argument that will pass into this function, right? So you reference targets rather than individual variables. And so the first thing we have to do is bind the buffer to the array buffer target, and then we'll buffer the data we want into the array buffer, and mode is going to indicate how often we want to read and write the data, which is going to make sense when we look at this function called down here. So the target is gl.arrayBuffer. You're always going to use the gl.arrayBuffer target with your vertex data. We create a new float32 array to take our plain JavaScript array and turn it into an array of only 32-bit floating point values. So floating point values are basically decimal values. And gl.staticDraw means that the contents of the buffer are static. So we're never or very rarely going to update them after we've buffered them, right? You can use gl.dynamicDraw or other ones like StreamDraw and other ones that I can't even remember right now to specify different modes of usage. And basically by indicating a usage mode, that can help the GPU optimize it so that we store it in a memory location that is most efficient for the type of work that you plan to be doing with the buffer. The index buffer is the same story, but instead we're going to use the element array buffer target. So we always use the element array buffer target to store indices into the vertex array. So that's why we use that for our index buffer. And we also store the indices as unsigned 16-bit integers. So that's why it's a uint16 array. And yeah, I went through that very quickly. So I'm sorry, some of you might be confused. If you are, ask a question in the chat. All right. I don't see any questions, but if there is one, just go ahead and let me know. So we're going to continue with our next topic, matrices. Matrices are a very important part of computer graphics. They're also kind of boring in my opinion because it's just math. It doesn't involve any of the fancy going between transferring data between CPU and GPU and drawing pictures on the screen and all that type of stuff. Niranjan asked, so is this handling data for the location? Can you unmute and clarify your question?
Yeah, I was talking about what the create buffer does. It like handles the data for the location.
Yes. So the create buffer, it does. It buffers all the data that we will then pass into a location. However, with create buffer, we have not yet bound that buffer to a location. So this is the first stage, which is passing the data to the GPU and storing it in memory. And then we're actually going to bind this buffer to the location later. Does that make sense?
Yes.
Okay, cool. Yeah, that's a really good question, by the way. And we will get to the part where we actually bind it very shortly after the matrices. So we're going to use a third-party library to handle our matrix math because I didn't feel like writing it myself, and this is already a very long and intense workshop. The third-party library that we use is called GL Matrix, and is very fast. It's a very good library. The person who wrote it was fairly influential in the development of WebGL, actually. So he knows, a lot of performance techniques and stuff. So all I'm saying is I highly recommend it if you're doing anything with WebGL. So the first thing we do is use the GL Matrix library to create a 4-dimensional matrix. And then we are going to apply a perspective transform to that 4-dimensional matrix. So GL matrix functions, the first argument is always the output. So the matrix that we want to apply the operation to. And we have the field of view here. So a typical field of view for a perspective matrix would be 45 degrees. And we multiply it by math.pi over 180 to convert that to radians, because we like to work with radians often in 3D graphics, right? When we're using a lot of trig functions and stuff. This is the aspect ratio, so the width of the canvas divided by the height of the canvas. And this is the nearest and the farthest z coordinates to the camera. So like if something is closer than 0.1, it won't get drawn, or it'll look messed up at least. If something is farther away than 1,000, a z coordinate of 1,000 units, then it also will get not drawn or messed up. Aditya asks, why 4D? That is a really good question. And as I maybe alluded to earlier when talking about the vertex shaders, I actually don't know. But there's certain types of transforms that are easier to perform by multiplying 4D matrices by 4D vectors, and then just taking the X, Y, and Z components of that result, or just the X and Y components later. So I'm sorry, I could not answer that question for you, but I'm sure there's plenty of information about it. If you look up matrix math for 3D graphics online, there's a lot of good resources. I feel like this may be related to the concept of quaternions, but I'm unsure. There is a lot of quaternion math involved when we get to animating models. So if you're trying to have like a person and animate them to walk, so it looks like they have a skeleton. So it is probably related to that. Yes. The view matrix now. The view matrix basically represents our camera transformation. So when we have a camera, we don't actually have the concept of a camera in WebGL. What we do is transform the entire scene in the opposite direction of where the camera is going, right? So for example, if I walk backwards, then what's actually happening is the entire world is basically pushed forwards, right? That's how you think of it as a graphics developer. So here so negative units are forwards into the screen, so basically being pushed inward to the screen, going farther away from us, the viewer. And so when we want to move the camera out so it looks like we're standing in front of the cube, we just push the cube backwards into the screen by 7 units. Otherwise, if we didn't do this, we would be standing inside the cube, which is an interesting effect. I can show you that later. And the model matrix here, the model matrix is transformations that are specific to the model. So in this case, there's only one model. There's the cube. But if you're working with multiple models, then it's very helpful to keep track of the model transformations separately from the view matrix transformations, the camera transformations, and that's why I did that here. Hayden asked a very good question. We don't actually move the objects in the world by changing the buffer vertices. The movement happens in the vertex shader. Yes, exactly. I'm very glad you asked that. So it would be extremely inefficient for large models, right? If we had to rebuffer the vertex positions every time we moved them. That's why instead we just apply transformations with a matrix, and we multiply the matrix by each vertex in the vertex shader. So let me know if that makes sense. But the answer is yes. The movement happens in the vertex shader because we transform the matrices that the vertex shader reads from when it transforms each vertex. And then the final thing we need to consider with matrices is I wanted to create a cool rotating effect so the cube is spinning around, right? So the way we do that is we reset the model matrix to its identity state. So if you multiply a vector by an identity matrix, you just get the same vector out. And then we rotate the matrix by a function of the time. And we rotate along the x coordinate and the y coordinate. Rotating along x, so x is horizontal. So if you rotate along x, it looks like the model is doing this, right? It almost looks vertical. If you rotate around the y-axis goes up and down. So the model will appear to be spinning around in this direction because you're rotating around that axis. And then yes, the model view matrix, we just create it here because we're going to use it later. And every frame will just take the model matrix and the view matrix and multiply them, and we'll write it out to the model view mat variable. It looks like you all kept the questions coming so far during the conversation, but let me know if there's any more about matrices. We're getting really close to where we can actually draw content on the screen. Rotating both is giving that effect in the beginning. Yes, you are correct. And And you know what? We can after we get through this, we will disable one of the rotations, and I'll show you what it looks like if we rotate only one. It's a very good question. The next thing we need to do is initialize our WebGL context. So the WebGL context, we have a viewport, which is basically tells WebGL how big the image is that we want it to render. And in this case, it's the same width and the height as the canvas element. We want it to fill the whole thing. We set the clear color, which is the background color of the scene. So this is almost black, but not quite. It's basically 10% brightness on each of red, green, and blue, and then 1.0, so it's not transparent at all. It's fully opaque background. And enabling depth testing, I explained what depth testing does earlier, but you got to enable it to make sure before you render any content to make sure that it's active. There might be times that you'd want to disable the depth testing as well. For example, if you're rendering two-dimensional graphics. So that's actually optional. That's not required. WebGL doesn't have to run as a 3D graphics API. You can use it for 2D graphics as well. And it will be faster than using a CPU-powered 2D graphics library. But here we want to do 3D, so we're going to enable depth testing. So finally, that was a lot of code, but we can get to the part where we actually draw the cube inside the draw scene function. The first thing we do is we use the browser's request animation frame API. And what that does is that tells the browser, okay, next time you're going to draw content to the screen, call this function so that I can update the content on my element, which in this case is the canvas. We call our animate model matrix function to make the cube spin, and we also multiply our model and view matrices to the model view mat variable that we declared above. We clear the color and depth buffers. So the depth buffer is invisible, but it basically keeps track of the nearest object drawn on the screen at any given pixel, and that is for the purposes of making the depth test actually work, because the depth test needs data to test against. The data it tests against is the depth buffer. We use our shader program. So we wrote the shader program and compiled and linked it earlier. Here we are actually finally going to use the shader program. We're also going to pass both of our matrices, our projection matrix and our model view matrix, into the uniform locations that we acquired earlier. So remember when we declared the uniforms in the shader, and we also stored the location, the ID of each uniform, into the shader program info variable. So now we can finally use that location and write our projection matrix and our model view matrix into the corresponding uniforms, so that the GPU actually has the content and can transform the vertices appropriately. Now our vertex position buffer, we already declared that earlier, so that's the big long array of all the vertices in the model. We bind that to the GL array buffer target. GL.vertex attrib pointer. So there's a long explanation of this function up here. It's a very flexible function, which is why it takes so many arguments and is kind of gross to look at. But GL.vertex attrib pointer, we pass in the attribute of our vertex, which is position in this case. 3 indicates it's a 3-dimensional vector, so there's 3 components for every attribute, x, y, and z. And GL.float. We're using floating point data here, not integer data, so we use GL.float. The rest of these, read the documentation I linked above if you want to figure out what they do. Basically, it lets you draw just a single part of the array if you want to. And enable vertex attribute array, so we just have to tell the shader that we are going to use the position attribute that we declared. If you don't have this, it probably won't draw anything on the screen, and it's really annoying, so make sure you don't forget this line. I used to forget this line all the time when I was coding WebGL, and I'd have like hundreds of lines of code and an empty screen, and it was frustrating. So remember to enable your vertex attribute array. Now we just bind the element array buffer, so our index buffer. Remember, we use the element array buffer target for the index buffer, and we invoke a draw call. A draw call is a very special type of API function in WebGL. A draw call actually draws content to the screen. So we've configured the WebGL pipeline earlier, and now we call draw elements. So draw elements references our element array buffer or our index buffer, and we tell it we're going to draw triangles, and the number of vertices we have is the length of the index array, basically. So that's going to be I can't remember what it was. I think it's like 72 or something, or 36 vertices. I can't remember. And then, but it's stored in a variable for us, so we don't have to worry about it. Basically, this is just the number of vertices that it takes to make a cube. unsigned short because we used unsigned short or unsigned 16-bit integers, and 0 because we want to draw the whole thing. So we're going to start from the very beginning of the buffer and draw all the way out. And yeah, then we just issue a window.requestAnimationFrame call to call the draw scene function, which will in turn call requestAnimationFrame for subsequent iterations. And go all the way back up to the top of the article, and you have your spinning cube. So thank you everyone for paying attention so far. I know Jafar wants to make his Willy cube, so we're gonna have to move on soon to part 2. We're talking about applying pictures and stuff on the cube. But Niranjan's question is the draw what converts the code into bytecode for the GPU? That is a good question. Actually, it is not. So the bytecode for our shader, we compiled in the compile shader function. So this function that we called earlier is what generates the bytecode. And the reason for that is because generating bytecode is actually a pretty expensive or inefficient operation. It takes a long time to convert text into bytecode. So we want to do it once and then just reuse that bytecode for future draw calls. So if you're aware, when we use the use program function to use our shader program, this basically just the shader program already stores the bytecode, and this says, okay, here's the bytecode we're going to use for this draw call. Let me know if that makes sense or not. Drop a yes or no in the chat. And great job, everyone. For the does anyone have any other questions? I'm going to wait for just a minute, so type fast if you have a question, or just unmute yourself. You're welcome to unmute yourself. All right, no questions so far. Well, great job, everyone. I hope you are tracking with me. If you're not, if there's anything you're confused about, please let me know, because really, these tutorials are available all over the internet. The value of you coming to the workshop is really just for me to be able to help you and walk you through anything that you're confused about that we're talking about here. So let me know if there's anything that you're confused about. If you just need more time to read about the API calls and stuff, then there's a lot of detail in this document. And you can also read about them on the MDN, Mozilla Developer Network WebGL reference. But if there's anything that conceptually you're confused about and you don't understand how it works, let me know. Let's just make one change real quick before we move on to texturing. So at the end of this workshop, you all are hopefully going to submit a pull request to a repository that will keep track of everyone who's participated in the workshop's content. And so, the cube above, we have this beautiful sort of strawberry pink color. It's kind of red. One thing you might want to try for customization is changing the color of the cube. Let's do that right now. We're going to make it blue. So you can see I changed the color. I changed the RGB values in the fragment color. And if I hit Shift Enter to apply my changes, or just click on there's a play button over here, which I can't see because there's zoom overlays. But yeah, you just do that and you go up and well, you have a purple cube now. It's not blue. I did not estimate correctly what those colors would do. But yeah, just put different numbers in there and see what it looks like. Also, for those of you who want to know more about buffers and how they work, and how vertices work, why don't we try changing one of the vertices quickly of our model. So do we need to fork this code? Yeah, you can, or you can just modify it in the current session and then download the code later, and I'll tell you how to do it. If we don't have time to talk about that, then you can, and you want to download it and you want to fork it or whatever, then you can join the voice chat in Discord afterwards. But where was our, geometry buffers. So our vertex position array, let's see if we just stretch one of these out to like 2.0 and save that. Then you see we have a vertex that is now in a different place than we would have expected it, right? That's good. That's because we changed it. So you can try changing those vertices and see what kind of different shapes you can make. All right, we're going to go to part 2 now. So Matthew posted the link above. Thank you, Matthew, for doing that. Let's get to part 2. So part 2 looks very similar to part 1, but we're just going to scroll down or do Control F, adding a texture. So you can see we're going to put a little squirrel face on here. But Jafar is going to put a Willy face on here, and the rest of you can all put different pictures on there. So we'll talk about that. So to add a texture to an object, we first need to load the image. So you have to create a texture resource bind the texture to the texture 2D target, kind of like we did with vertex buffers. We had to bind them to a target. You have to do the same with textures, because a texture is just a type of buffer that is used to store image data. We flip the images upside down because the coordinate system in WebGL works different than the coordinate system in like Photoshop or other tools that are used to author the textures. And we use gl.textImage2D to put data into the buffer. So this is the equivalent of a gl.bufferData call, but for a texture. And the rest of this stuff, I'm not really going to go over. You can read all about it in this document. Other than mip mapping is a really cool technique that lets you get accurate downscaling. So if you zoom out of the object and it's far away, and want to use an accurate scaling filter to make it look more precise and smooth and stuff as you're zoomed out, then mip mapping allows you to do that. So yeah, we're going to use our load texture function to load to load this image so that we've uploaded here into a texture on a WebGL texture. Are there any questions about that so far? I know I didn't really cover the code line by line, but is everything okay? Or do you have any questions about the specifics of what this does? All right, it looks like no questions, so I'm going to keep going. But if you do have a question, just go ahead and finish typing it and send it whenever you want. The next stage is to add shaders. We're going to update our shaders. So we had a position attribute earlier. Now we're going to add a texture coordinate attribute. So every vertex, when you're texturing a model, every vertex has a texture coordinate. And the texture coordinate basically indicates what pixel of the texture maps to that vertex. So a texture is imagine we took like a sheet of paper or something, we stretched it all around an object and we like glued certain positions of it to the object. The texture coordinate is basically what position of the texture did we glue to that vertex. Look up some stuff about texturing if you don't understand that, because it's really hard for me to explain. For some reason, I'm not good at explaining the texture coordinate system. But we also have a new varying Vtex coord. So Vtex coord varyings let you communicate between vertex and fragment shaders. So you can see our vertex shader, we simply set the value of the varying to the value of the texture coordinate. And in the fragment shader, we can read the value of that varying, that texture coordinate. We also have a new uniform called texture img, and that is our texture image. So sampler 2D is basically an image that we can read from, and we use the texture 2D function to read the color of that image at the texture coordinate that we are looking at right now. And you do that, and then we also have to remember we have to update our shader program info object with the texture img, and we have to create a new geometry buffer. So this is like we had a vertex position array, we have a vertex texture coordinate array as well, which looks like this. Lots of data, but again, your favorite 3D modeling tool will actually just spit out this data for you, so you can copy and paste it in, which is nice. And we call our create buffer function that we created earlier to buffer our texture coordinates. And the draw scene 2 function is the same as the draw scene 1 function, except we bind the texture. So you get texture slots. You get 0 through 15. So normal GPUs, you get up to 16 textures can be active for a single draw call. And here we're going to use the first one. And some GPUs will give you more. But for now, we're going to assume 16 because that's the same assumption, or like a safe assumption across multiple pieces of hardware. Once we have a texture activated, we can bind our 2D texture, our texture to the texture 2D slot, and the texture 2D slot is actually affiliated now with the texture we activated. So you can have up to 16. And gl.uniform1i, we're going to pass in our slot ID, texture 0, so that's where the 0 comes from, to the texture img uniform of the shader. We also, just like we bound our vertex position buffer up here, we bind the texture coordinate buffer in part 2, and that's a two-dimensional vector, so we use a 2 rather than a 3 there. And we've done that, so we're going to call draw scene 2, and you have a cube. So there was a lot of good questions during this session. I'm going to go back and try to reread through them. Niran John asks, how is the cat image on each face of the cube? That is a good question. So every face of the cube is rendered with the same texture because we only bound one texture, and the texture coordinates from 0 to 1, every face basically has valid texture coordinates for each vertex. So we've basically mapped the texture correctly onto the cube, and so onto every face of the cube, and so every face of the cube renders with the same texture. If we want to render different textures on different faces, there is a way to do that. One thing could be to create a big texture that has multiple like subtextures, and to change the texture coordinates for each vertex on each face, so that you're referencing only a sort of a little slot of the texture that, or a little portion of like the bigger texture. Another way would be to draw all the different faces individually in with different draw calls, but that's not very efficient. It's easier to batch them and use one large texture. Also, Hayden asks, what happens if you assume there are more texture slots than there really are? Will GL figure this out, or will everything break? I think if you assume there are more texture slots than there really are, you'll just get an error, and it won't work. GL can't really figure it out because it's actually a limitation of the hardware, not of the software. But it won't break in the sense of like your computer blowing up, right? No, you're not going to damage any hardware just by experimenting with WebGL. So that's one thing I would really like to tell everyone during this workshop is do not be afraid at all of trying anything you want with WebGL, because you're not going to break anything irreversibly. Your code might just not run, and you have to modify stuff later. And yeah, don't delete your system32 folder or your OpenGL driver or anything, though. That would be weird. Is there no equivalent of gl.get integer v in WebGL? Okay, so it sounds like you have, Hayden, you have some experience with OpenGL already. It sounds like I'm pretty advanced, perhaps. Yeah, there is an equivalent of gl.get integer v in WebGL that will actually tell you how many texture slots there are if you pass in the right arguments, but I didn't cover that in here because it's unlikely that people are going to need to get more than 16 textures. So yeah, if you want to upload your Willy texture, Jafar, you're going to go to the top of this observable document, and you're going to click on the 3 dots, and you're going to go to File Attachments. Okay. Now here you're going to drag and drop a file from your File Explorer onto this thing where it says drag and drop files to this panel, and it will show up a new file name here. So like this is texture.png, you'll get a second file with a different file name. And you'll go scroll down to the place in this document we had texture.png, and you will paste in the name of your new texture that you want to use instead. And if you do that, you should have Willy on the cube. And if you get Willy on the cube in the remaining 15 minutes or so we have for the workshop, then send everyone a chat message because I want to see it. Are there any? Yeah.
So can you go back and show me how you did that again? I wanna, not a Willy face. How you added how you showed him how to add the Willy face.
How to upload the texture.
Yeah, how to upload the texture.
Yeah. Let's do that. So we go to File Attachment, and we're going to open the Pictures folder and get I don't know, let's just take a picture of something. And let's take one of these, and we're going to drag and drop it over here. This is like not a good texture, but this is just a picture I had on my hard drive, right? Yeah. So we go ahead and upload it. It might take a long time.
And then after you upload it, you just put that file name instead of texture.png, right?
Yeah. We'll watch once it uploads. You'll see what happens.
All right.
It's taking just a second to upload, but if we take this file name, and we're going to go down. So if you do Control F to search, you search for texture.png right here. And we're going to paste in this file name instead and run. And then you should see up here we have a different texture on the cube, right? Like an outdoors texture. So that's how, if you do that with a picture of Willy, then you can get your Willy cube.
Yeah, I'm not going to do that with Willy. I think I'll let Jafar do that.
Yeah. Well, yeah. Sorry, I don't have a picture of Willy handy. Oh, Aditya did it. Very nice. Neil did it as well. I'm glad to hear. I hope you guys can post some screenshots of that in the Discord sometime soon. All right. Thank you for letting me know. I'm excited to hear about y'all's success, and you can definitely commit that as well to the final repo where everyone will be committing their stuff. So I want, if we have time, because I do think we're going to go over time a little bit. Matthew said that would be okay. I want to really quickly go over lighting. I can't go over this in a lot of detail, and I'm sorry this workshop has been a little bit has been quite chaotic. But I do think lighting is a cool effect, so I want to discuss it quickly if we have time. So you can see what we are going to do with lighting is shade each face of the cube differently. We'll have like a light source facing it. And so let's go ahead and jump into the code to do that. And like I said, I've gone pretty fast, so you're just going to have to interrupt. Let me know if you have any questions. I see the chat is blowing up, so let me check that out first. If y'all aren't done yet, can y'all move the workshop to Discord? We need the Zoom to do another one. Yeah, so
I got it to work, George. I put a Fall Guy model I made.
Great job. I'm glad to hear it. And Neha sent us a screenshot, so I'm going to download that and take a look at it soon. I think we need to move to Discord right now. So if you want to go in a voice chat channel on Discord, would that work for you?
Yes, George. Good. So I want to commit this.
All right, cool. Yeah, thank you so much. I'm glad to hear it. I'm sorry for the inconvenience, but we are going to have to leave Zoom for now and go move over to Discord. But I will be there. So if all of you are still want to be in this workshop, or for whoever wants to be there, just move to Discord. I'll find whatever channel y'all are in